Welcome to this talk. My name is Upmanu. I'm in SCAS and at the Walton Institute at ASU. I've been here for about a year. And I'm happy to discuss this idea that we've been floating around for a bit now. In terms of the talk style and so on, if you want to stop me as I'm talking, that's totally fine. Basically, the idea here is that we all face the impacts of climate extremes around the world. It's a global problem. I'm not interested in climate change per se. I'm interested in climate extremes and what to do about it. And the idea that we are putting forward. No? Here. Okay,
Yep.
got it.
Okay.
Yeah. So we are calling it weather jiu-jitsu, which is the idea of can we use the power of the atmosphere to control the atmosphere rather than trying to make huge changes in the game. So it'll be interesting to see what you guys think of that as we go through. So what I'm going to do in the talk is we'll talk a little bit about climate extremes, give you some examples, and what I'm working towards is the idea that a large variety of mid-latitude climate extremes can be connected to basically exactly the same mechanism. So that sets up the idea that if we can mess with that mechanism, we have multiple gains to be achieved associated with that. So that's what we are setting up. I'll talk a little bit about the role of geoengineering or decarbonization. And the main point I want to make there is even if we succeed there, climate extremes and their impacts are not going away. We still have to deal with that. And that's the motivation for what I'm talking about. In short, this saying is attributed to Mark Twain. Everybody talks about the weather, but nobody does anything about it. Turns out, actually, it's not due to Mark Twain, but one of his buddies, Charles Dudley Warner, who came up with that, and Mark Twain appropriated it, and of course, got famous with that. So the thought is maybe we ought to be thinking about that as our plan for the 21st century is how do we actually monitor the weather? And the argument I make in short is this. Historically, we have spent billions of dollars on building infrastructure to protect us from climate extremes. We didn't have so many people then. We now have a lot more people, a lot more exposed, and most of the stuff that we built in the previous century is now aging and needs to be replaced, and the replacement cost is in the hundreds of trillions of dollars, which is not going to happen. So if you're thinking about spending that kind of money at all, we should be looking at alternatives. So the last part of this is like, okay, how are we going to do this? And we take the inspiration from the idea of chaos theory or sensitivity to initial conditions, which traditionally has been presented as, hey, the weather is not predictable because the equations that govern it are nonlinear, small perturbations amplify, and so you're lost. So the idea here centrally is, okay, we can't predict, so we are screwed on that front. However, if small perturbations amplify, maybe we can introduce small perturbations deliberately and then see if they can amplify in directions we want them to go. So that's the idea. And so what I'll show you is that we are able to demonstrate, and others have demonstrated this, that in idealized models, we can do this very well. The question is how to make it happen for the real jet stream dynamics, and we'll just be speculating on that at the present time. So getting started, this is a time series which is kind of interesting. That's put out by climate.gov in this particular case. And it illustrates losses associated with billion-dollar events. So each event in question here ended up with a loss of at least $1 billion is the idea. So that's the y-axis on the left-hand side. The actual total cost is on the right-hand side. And you can see that this has been growing dramatically. But more importantly, if you look at the colors, what you see is that the dominant factors are storms, tropical cyclones, and floods in that order. Droughts are talked about a lot. Droughts are this little orange thing at the bottom. So what you see with droughts is that our drought losses in the United States are relatively constant every year. We always have a drought somewhere or the other. It's not something that is spectacular, but the other things have been increasing. So people view this as a climate change problem, and we'll be talking about that in a second. Okay. Second thing here is that this observation, and this is from group that is putting together information from the reinsurance companies. And they point out that everyone focuses on the big event, but what's been happening is that the cumulative losses associated with smaller events that people don't talk about nearly as much as what's been going on. So we will discuss that a little bit further. And that's here. This is from Roger PLK Jr. Somebody wants, okay, should have care of it. This is from Roger PLK Jr., who is the son of Roger PLK Sr., which makes sense. Roger PLK Sr. is a card-carrying meteorologist from Colorado State University. Roger PLK Jr. is a social scientist who's a climate change denier, which is an interesting domestic situation, perhaps. But what he presents here is a typical picture that he has presented again and again every few years. And the picture is, he takes those losses that were in the previous picture, he divides them by the GDP, and then he shows that they are modestly declining. Okay? So his view is that, okay, the reason these losses are going up is because we have more exposure. We have more property value, we have more people through climate change. That doesn't exist. Okay. My reaction is I don't really care to join that argument. I have a personal view that one of these people is inherently stupid, but we won't get into that. My point is this. If we think about what this guy is really showing, he's saying even if you manage carbon better, even if you solve the carbon problem, as GDP grows, which we expect it will, and as the populations grow, which we expect they will, if the percentage of GDP is constant in terms of losses, which is what he's sort of arguing, then we are still going to have those losses. Those are not going away, even after decarbonization. So we need to address that particular problem. And what's our strategy for doing that? Okay, so to kind of get started on thinking about that, the first lineup that I have here is we have 92,000 dams in the US. The median age of these dams is now 67 years. 5,000 of these are owned by the federal government. There is a budget behind it, and we think they are being maintained, although some people question that. What about the other 87,000? These are owned by municipalities, owned by states, owned by private companies. And to give you just one example, there are about 100,000 of these dams in the state of Pennsylvania, and there are 3 dam safety inspectors. Data on how much money is being invested in keeping these afloat, non-existent, okay? So that's a concern. So now here what you see is that since the year 2000 up to 2023, which is when we finish this work and publish the paper, 552 dams had failed in the US. So that's about 1 every 2 weeks. Now, arguably, these have not been large dams, but that's part of the story. There's a log scale as to number of dams versus size of dams. As the size of dams goes up, the number of dams goes down. So the question is, when you talk to the dam safety organizations and to the engineering community, we design these dams for the 1,000-year event or the 10,000-year event from failure. So one failing every 2 weeks is not a good story. What's the return period actually associated with the rainfall that led to the failure of these dams? So that's what we investigated. And you have a bunch of different plots here. Just focus on the bar graphs for now. And A means that how big was the rainfall event associated with the failure event on the day of the failure, or the largest day preceding the failure of the failure event. Okay, so that's A. K5 means that you look at the 5 days preceding the maximum rainfall and how much that rainfall was. K30 is the 30 days preceding. So if you look at those, what we see is that those return periods, that's 100, these are around 5 or 10 years. Very, very far from the 10,000-year design that people are talking about. So what people are talking about now is that under climate change, how will the probable maximum precipitation or the 10,000-year event change? And what we are finding is that things are failing at very modest levels. So there's no point talking about the 10,000-year event when you have failures at this time. Story changes a bit when you look at J5 and J30. What that refers to is what's the probability of exceedance of both of those things happening. The rainfall on the largest day before the event of failure and the 5 days preceding that, or the largest event and the 30 days before that. So those are starting to creep up close to the 100-year event. Still, nowhere close to what we are talking about as failure. Most of the climate change attribution literature is focused on, has the one-day rainfall event gone up? Has the 1-hour rainfall event gone up? What we are seeing here is the joint event of wetness, followed by a wet event that's leading to the flood. Similarly, okay, so we covered that. This is data from the National Flood Insurance Program, which is, by the way, insolvent at the moment. Okay. The National Flood Insurance Program in the US is designed so that everybody who's in a 100-year floodplain has to buy insurance, no choice. Okay. So that's the idea. There are 3 frames here that we look at. The first one is insurance claims. These are at the household level, aggregated to the county level. The second one is presidential disaster aid declarations. And the third one is money put up by the federal government or a state government to buy out people's property who are in locations which are perpetually getting flooded, so they want to pay for it anyway. Okay. The bar graphs show you the return periods associated with these claims. Remember, the design is a 100-year floodplain. The median return period associated with these rural, suburban, and urban are the 3 colors, is around 5 years or less. So it's not the 100-year event we are worried about. We are having a lot of payouts of these things, and that's leading to the insolvency of the program. Okay. There's more on this story, but mostly what I'm trying to create the picture for you is that it's really, obviously a major hurricane is a big threat. We have to worry about that. But we are actually getting significant losses associated with relatively modest events. If you go and examine the nature of those modest events, these are fronts. These are frontal mechanisms that are bringing those kind of storms. Persistent input of moisture into the area, followed by an event that crosses a threshold of some sort.
It's also the case that urban settings are designed for very low return periods.
Yeah.
So, I mean, we're used to designing dams for extreme events.
Yeah.
Urban drainage is
2 years or 5 years.
Yes. Yeah.
So if you see, the urban guy is at 5, the rural guy is at 2. Yeah. So it's happening every year to some of these people. It's crazy, basically. And as you would expect, presidential disaster declarations have a larger return period, but still it's not anything that we would not thinking about. Okay. So our de facto adaptation strategy, this is what I wanted to summarize with. We have aging dams that are failing. We just need a major dam to fail, and people will wake up on that, and that luckily has not happened, although we came close in 2017. We have a flood insurance program that faces insolvency at this moment, and all attempts to change that transfer the risk onto the people that they are currently protecting, so people are not happy about that. So that's kind of our strategy. Moving to other types of events from floods. This is the Great Texas Freeze, February 11 to 2021. The damage associated with this event was $200 to $300 billion. It exceeded the largest damage from a hurricane that we have experienced. That's to give you a sense of the scale associated with it. Electricity went out, that affected 10 million people. Water pipes burst everywhere, so there was no drinking water supply. And 200 people died, 3.8 million fish, so there's an ecological dimension to it, and transportation impacts. It was presented as unprecedented and an example of what climate change is doing to us. So the paper we published actually looked at, this is 2021, the event in question, 1-day, 3-day, and 5-day temperature profiles associated across the country. So you can see this deep freeze that happens over the midsection of the country and is represented at all 3 time scales. But if you look up, we have 2011, 1989, 1983, 1951, all of them with very similar events. There was no excuse for a lack of preparation. Okay. It could be climate change, but it's hard to make that argument. Okay. What causes this? I'll be dwelling on that in the next few slides. It's caused by a very deep trough that basically comes down from Canada into this area and brings cold air down and persists. Okay. Part of the jet stream dynamics that I'll be building up. And you saw this happened at various other events. If you don't care about Texas, but you care about Kansas, if you care about Missouri, you'll see that this is a very routine event in those places. So what is the jet stream? Basically, most of you probably know, but just for completeness, we will develop that idea. The thermodynamic engine for the planet is basically at the equator. That's where you get most of the heating. So you end up with convection, and quite a bit of that heat needs to now be dissipated to areas which have lower temperatures. So if I look in this direction, basically I'm looking going from equator to pole, because the pole is the other endpoint of this particular engine, because it's until it all melts, it's a constant temperature location. So that's basically what defines this particular heat engine. And what you end up with is a convection cell here that's called the Hadley cell, a synchronous cell here called the Ferrel cell, and a polar cell. And looking in this direction, this is the location corresponding to the subtropical jet. That's the location corresponding to the polar jet. And the features associated with this are what I was developing. This is our top view looking from the pole as to how the winds are organized. And I can talk a bit more about it, but there's a nice little video that I will show you. The basic thing that happened for Texas was that if the polar vortex is stable, the cold air is contained within the polar jet stream, as is shown on the left. But if it is disrupted such that you end up with this big wave in the polar jet stream, you end up with a cold, warm, high, low pressure sequence associated with it. And that's essentially what was the story associated with that particular event. Similarly, if I look at heat waves, yeah, this is the UK, and this is from the UK Met Office. They were trying to explain why the last week there was hot, and what you see there is the curvature of the polar jet stream is way to the north, so you end up with that situation. And if I expand that further, you get synchronous heat waves or freezes across the whole planet, depending on what's called the wave number associated with the jet stream, which is how many waves around the world, how many high-low sequences you get around the world. So if we start thinking about these extremes, then what we are going to end up thinking about is the manner in which this particular system basically works. So here's some dynamics associated with it. Things respond to boundary conditions and to initial conditions. That's how in physics we have started to learn about how these systems work. So in this particular context, what's being shown is what happens to the jet stream dynamics during El Nino conditions in the tropical Pacific versus the opposite side of that, which is La Nina conditions. And essentially what that does is it changes the equator to pole temperature gradient. It changes the land-ocean temperature contrast. And then those two features combine to determine where the mean position of the subtropical jet and the waviness of it is manifest. So that's one example. As we do global warming, we end up with a weaker equator to pole temperature gradient because the poles warm much more than the equator. So that leads to a condition which is almost like a perpetual summer, a weaker jet stream, and a shift in the jet stream location. So boundary conditions are important from that point of view, but I'm going to focus on the weather time scale rather than the climatic time scale. So I wanted to show you this.
Back in 2010, Russia experienced one of its most severe wildfires and heat waves, while Pakistan witnessed its super floods, of which the 2022 flash floods are a cruel reminder. While these two events were over 2,000 kilometers apart, they were connected to a single meteorological event, the Rossby waves, named after Carl Gustav Arvid Rossby, who first identified them. While these events were different in nature, the waves caused a high-pressure pattern over Russia while influencing downstream wind patterns in the Indian subcontinent, leading to the floods. But what are Rossby waves and why have they gained relevance over the last decade? Rossby or planetary waves occur within the Earth's ocean and atmosphere. They move continuously along with the rotation of the planet. These can be classified into two categories, oceanic and atmospheric Rossby waves. Unlike surface tidal waves, which break as soon as they touch land, Oceanic Rossby waves are found along the thermocline, or the layer where the warm surface waters mix with the cool, deep waters. They move about in slow, undulating waves for hundreds of kilometers in the westward direction. It can take them a decade or more to cover the surface area of the ocean. Their interaction with phenomena like the El Nino influences climate across the world, sometimes causing high tides and coastal flooding. Atmospheric Rossby waves are high-altitude winds in the mid-latitudes. When the Arctic jet stream becomes more wavy and flows into lower latitudes, that meandering is referred to as Rossby waves. When they swing up, they transfer heat from the tropics to the poles, and when they swing down, they carry cold air towards the tropics to maintain some balance in the atmosphere. Any anomaly in Rossby waves can cause disasters in seemingly disconnected parts of the Earth. Normally, these waves move eastward, which implies that weather systems move with them. But if this eastward movement slows down or freezes, then high and low pressure areas persist over specific regions, like they did in Russia back in 2010. While the wildfires and superfloods did not happen together, their impacts were felt around the same time. Rossby waves are composed of two intricately linked types: synoptic and forced waves. Synoptic waves move quickly, only formed by the atmosphere, but they also contain minor static or forced components. Forced waves are formed by interruptions of mountains and temperature differences across continents and oceans. These contain minor synoptic components as well. These two types interact with each other within an atmospheric channel called a wave guide. This interaction allows their strength to increase and influence the weather. This interaction is also called wave resonance. While we do not have extensive historical data on Rossby waves, a lot of events like the 2003, 2006, and 2015 European heatwave, Balkan floods of 2014, US heatwave of 2011, and North American heatwave of 2018 have been attributed to them. Research is still being conducted on the definitive influence of anthropogenic climate change on natural atmospheric phenomena like these. It shows us how small and delicate changes in atmospheric phenomena lead to catastrophic events affecting the environment and society at large.
Then there are transient components where something, even if you have a string that's constant, if something bumps it, it's going to resonate associated with that. So the combination of those two, forced as well as stationary waves, is what these things correspond to. And that's essentially the idea that we want to do. Okay, so the model here was the interaction of these planetary scale wave jet stream dynamics with local features determines the scale, persistent, and location of climate extremes. So the climate extremes I introduced you to so far were the freeze, the floods or storms, and the heat waves. So all of those in the mid-latitudes will now essentially be related to this phenomena. And the other point I tried to get across was that we are used to thinking about what's going on here. But what's going on here is related to many other places because of the same mechanism. So if we can mess with this mechanism, we have the ability to influence the whole wave train. And that could be good or bad, because we may affect positive change here, but it may end up with a negative change somewhere else. So you have to think about how one does that. Okay, so this is just the illustration of the same process we looked at. So let's actually move forward. So this is now going to be a section on atmospheric rivers, which I got introduced to in 1992 by a paper from Xu and Newell from MIT. They did an analysis of satellite data and they identified these filaments of water vapor that were moving through from basically 5 locations in the tropical oceans. And then it's like a hose. So it starts here, but it can spray there or it can spray here because of the way it intersects with the atmospheric circulation. The instantaneous discharge in these features, like the one that you're seeing spin out there, is 2 to 3 times the typical discharge of the Amazon River, which is the largest terrestrial river. So that's the importance of these. And there's an example of a flood in California that happened because of this. So the reason I put this up is that in our group, we are taking the atmospheric rivers as the first demonstration target for can we actually control what goes on. So can we steer these rivers in a direction by nudging somewhere? Or can we smear them out so that the landfall is over larger area so that we diffuse the flood potential, but we provide the water. So that's kind of the goal. And here's another video. Let's see if this will play.
In 1862, California was hit by a mega flood as a result of continuous atmospheric rivers. It rained for about 45 days straight in Northern California. About a quarter of the state's real estate was destroyed, and a 6,000 square mile inland sea formed in the Central Valley. The state's capital had to be moved to San Francisco due to flooding. Remember that California's population was about 1% then what it is now. The USGS in 2010 created a scenario for a similar storm hitting California, which happens on average about every 200 years. The report also found that a similar storm to 1862 would force 1.5 million Californians to evacuate, and it would cause more than $1 trillion in economic damage in the long run. The report also outlined which major areas of California's cities would likely be inundated and have to be evacuated. Findings included that the majority of the people in the San Joaquin River Valley would have to be evacuated in this scenario, and it's possible that an inland sea would form again in the Central Valley, as it has time and time again.
Basically, what the story is in that video is that around 2008 or 10, the US Geological Survey came up with this idea called the Ark storm scenario, like Noah's Ark. And the storyline on this is the following. There's a group at the University of California, Santa Barbara, sedimentologists. They started investigating sediments and looking at the abundance of flooding that happened at different times. And this was motivated by the fact that there was an event that this video is talking about in Central California, where much of Central California, Central Valley was flooded for about the whole season, basically. Continuously in 1862, and Sacramento had to be evacuated. The state of California government moved to San Francisco, and their argument is that if the same event were to happen today, you would have to evacuate 1.5 million people from that area, and the losses would be in the tens of billions of dollars. And it's not here that we could restore the conditions anymore. So the USGS then looked at this, and from the sedimentary analysis, they figured out that in Central California, this kind of event has happened on average once in 250 years. So it's not, again, climate change, but it is something that we face. And the 1862 event was marked by the fact that you had streams of these atmospheric rivers coming one after the other. So the wave train was locked in position, similar to what happened with the freeze for 7 days, but in this case, it was locked in for the whole season. So every 4 or 5 days, there was another atmospheric river landing. And so the supply of moisture was continuous, is the idea. And so that's kind of the motivation for looking at this guy. Moving on to the East Coast, there our issue is hurricanes. And there's been quite a lot of work done in the past on how do I stop a hurricane? So that work falls into 2 categories. One is the hurricane is here, and the hurricane is sustained only if the surface temperature of the ocean is warmer than about 26.5 degrees Celsius. If it drops below that, then there isn't enough energy to sustain the hurricane. So there's a bunch of people who've tried to come up with creative ideas on how to bring up cold water up or to otherwise change the thermal characteristics of the system. There's the second major attempt to diffuse a hurricane has been to look at the wall of the hurricane and to seed, do cloud seeding kind of activities there, with the idea that by reducing the temperature to, or changing the temperature profile there, you can blow out the wall of the hurricane, and you do that. There has been modest success with both of these efforts, but the cost is prohibitive. And there was one event in which things actually went a little bit crazy, so they stopped doing that. Now, the reason I'm showing you this is, my argument would be this: these people looked at the problem all wrong, because their goal was to diffuse the hurricane. They're thinking in terms of a science experiment rather than protecting people. If the hurricane stays in the ocean, I actually have no issue with that from an engineering point of view or from a social point of view. So if you look at, and I can show you hundreds of these pictures with the hurricanes, in this particular case, this is this hurricane, and those are the jet stream winds. So this is going to actually be steered away by those jet stream winds in that particular direction. So this is an outcome which doesn't concern me. Here's another one, different hurricane, same story. So in the early 2000s, we built a stochastic simulator for hurricanes using a Markov renewal process, and it was intended to be a simulator for, just continuous simulation so that you get a risk profile associated with hurricanes. The student who worked on it started running it on live hurricanes as a forecast simulation model, and my reaction was, are you crazy? And I was made to feel really stupid when she actually predicted that Hurricane Sandy was going to have a landfall in New York, which only one of the 10 physics-based models was predicting. And I was going, we have no physics in this model. This is purely a stochastic model. But as we looked at the hurricanes and we looked at what our model was doing, there was a selection process in the model where if the hurricanes that it was sampling from had tracks associated with this, and we went and looked at what was going on in the atmosphere during those hurricanes as opposed to other hurricanes, it was exactly the steering winds of the jet stream that were involved. So if the jet stream had been going way off there, this thing has a landfall because there's nothing steering it away. If the jet stream is coming and curving way up, you have a landfall going in that direction. If the jet stream is doing what it's doing here, it's gone. So now that's tying together all the things I raised in the beginning as important climate extremes in terms of losses, and all of them then have a connection to how the jet stream behavior works. Okay, so I have thought through what we are doing on climate adaptation because this became a big thing because of climate change. And my answer is diddly squat. So we don't have a story. So even if we, I said if we decarbonize, we will still have these issues and we actually have no plans. A lot of money is being spent on green infrastructure, natural infrastructure, all that is needed, but most of that doesn't address the things that I've brought up. It doesn't address losses in particular at the scale that we are concerned about. I talked about these, and then in terms of even early action, the whole issue of lack of predictability, sensitivity to initial conditions gives us very limited ability to predict that. My colleague, Dan Schrag at Harvard was trying to get me to show up today in India because he's very concerned about the heat waves in India. And his proposal was that I join him in talking to Prime Minister Modi to make 1 billion people in India live underground because he doesn't see any other solution for them. So think, I bring that up because if you question the idea of perturbing the weather, you have to look at the kind of things people are proposing as an alternative to that. Okay, so this is my argument. We need a new 21st century approach, and we are arguing that this is weather jiu-jitsu, and I will try to explain how that works. So here's an idealized model, which is typical in any elementary chaos theory textbook. What is it? What it is the three variables that you're looking at. X is the mean velocity of the jet stream, and Y and Z are sine cosine phase of eddies or transient waves that intersect with it. The way this model works is that if you just look at this term here, dx dt is minus x, so it's purely dissipative. Okay. Depending on the magnitude of x, dx dt is negative, and so it's going to drive x to 0. It gains energy from the eddies at some rate. Okay. What does the eddy do? The eddy is dissipative as well, and it gains energy from the jet stream. So that gives you the nonlinear oscillation that's become the canonical model associated with this. So that's the structure here, and this is the typical butterfly that perhaps everybody has seen. And as this thing is going around, what I'll mention is you have these two areas which look like almost circles. So there's an oscillation happening in each one. It's actually fairly stable. And where the unpredictability or the divergence comes is as you jump from one wing of the butterfly to the other. Because think about it, if you're traveling here, you suddenly have the possibility of staying with this travel or jumping to the other side. That's as far apart as you can get. And that's where the problem comes with this particular model. Okay, so the idea of the Lyapunov exponents can be explained as here. You have two initial conditions there at delta zero. They're separated by that delta zero value. Then as the system evolves, these trajectories diverge. So the exponential rate of divergence of these trajectories with time, which is how delta t grows as a function of the initial delta O. And the Lyapunov exponent you see is delta t is delta O e lambda t. So lambda is the rate of growth of this divergence. Okay? So that's how this behavior happens overall. But we can actually look at how that is changing locally over the overall attractor. And so what you can see is that there are places where things are actually not at all diverging. These are negative values of that Lyapunov exponent. And what you can see is that those are at the edge of the attractor. You can't just go to space. You have to be constrained, so you come back. And then this is the area, as I said earlier, where you have the highest values of the Lyapunov exponent. So if you think about this in terms of sensitivity to initial conditions, these are extreme values here. I actually have pretty good predictability there. Where I don't have predictability is when x is approaching zero, so I have sort of an unstable situation. Okay? Very interesting to think about in that way. Okay, so there are local Lyapunov exponents which are calculated at a particular position in phase space, and there are finite time Lyapunov exponents where I can look at where I am today. It's closely related to the Lyapunov exponent, but I look at what my near time evolution might look like. If you know the equations, this is fairly straightforward to try to do. The second model that Lorenz introduced that's not as common in the chaos literature, but is foundational in the meteorology literature is the Lorenz 1984 model. It's very similar to the other one. The main changes are in these F and G terms that have been introduced. This represents the equator to pole temperature gradient as a forcing to that jet stream. And this represents the land-ocean temperature contrast as an asymmetric forcing to the eddies, basically. But otherwise, the model is fairly similar. So if we want to think in terms of this idealization of the jet stream, because essentially the Rossby wave dynamics are what these models are generating, this gives us a way to then think about how we could introduce our perturbations. And the perturbations can be introduced in the F and G terms, which are the boundary forcing. If I want to study the behavior of El Nino together with the jet stream, we have published on that. And we can take idealized models of the El Nino Southern Oscillation as an ocean-atmosphere interaction, and then use that to force F and G in this particular model, and you have a coupled model, idealized coupled model that goes through. So the idea now is to do adaptive chaos control. And so what the jiu-jitsu part of the argument is that this thing is losing predictability or deforming anyway. Let's just use that. We don't have to do a whole lot of work to do it. So if you think about the hurricane example that I gave you, all the people who worked on the hurricane worked on the hurricane and at that location. The argument implied by this is that if I want to change the jet stream, I'm probably going all the way to the Pacific for an Atlantic hurricane to induce the change way upstream, which then propagates forward over time and changes the dynamics. And it would be a small perturbation of some sort. So the adaptive aspect of it is that as I introduce these perturbations, I also have to see what happened. And then I do an update through data assimilation and move things forward. So that's basically the game. And the question is, can we control the trajectories for the Lorenz 63 or 84 model? And Moyan, who's sitting right there, and Shin, who is not. The other ones, oh, there she is, yeah. You're hiding behind the other person. So they've been working on this. And so basically what they have done is they have set up an optimization model just to see the feasibility of the game so far. So you apply a perturbation, but you want to minimize the total energy that you are putting in. And subject to controlling the trajectory of just the jet stream in this particular case, you could expand that. And so you look at a time forward and you say, I want to keep it right there and see if that's possible or not. And the energy is defined in terms of perturbations in X, Y, and Z. Those are the decision variables. So here's their result for the Lorentz model. And what they specified here was that they restrict the trajectories to stay in the positive quadrant. So it's a pretty broad zoom. It's not, restricting to a fine window. Left side is the natural evolution of the Lorentz 63 model over 2000 time steps. The right-hand side is the control version. So you can actually do that. And you can look at also cases where this fails. So it depends on the initial condition. You aren't always going to be able to do this. And learning when you can and when you cannot is part of what one needs to explore. And then here what he's got is the total energy of perturbation and the associated Lyapunov exponents, and they match, which is what you would expect. And then what's the percentage of the energy of the system that you are actually working with? And you can see that those are 0.02%. This is very small. So that was kind of the hypothesis associated with trying to play this game. And the Lorentz 84 model, the same game, and a similar result associated with that. And then in this case, the perturbation that you end up having to apply is quite a bit more. It's starting to approach 1% associated with it. But if you look back at the journey associated with the attractor that has been suppressed, it's also quite substantial. So this is how far they have gotten so far. And what we are shooting towards is first of all, a more realistic modeling strategy. So we take high resolution historical weather forecast, reforecast data on a bunch of attributes. We don't want to run a GCM because there's simply no way to do an optimization on that. So we use an AI/ML space-time emulator that's a pre-trained model. So you're just calling it there. And then you do an ensemble with that. You run the optimization, you look at the feedback and basically see if we can actually control these things. And the target is the atmospheric rivers in the Pacific. And so that's a data set that's been processed and it's available to us at this time. And what you're solving for, different from what we did with the Lorentz model, is the strength, location, and timing of the perturbation. So in the previous one, we allowed a perturbation at every time step. Now we are wanting to minimize the number of interventions that you also do in addition to everything else. Then to steer this or to precondition it, we would calculate these finite time Lyapunov exponents and use them to provide a prior distribution for when to do these perturbations and how much they should be. And there will be a regularization aspect to this as well, so that you're not doing this kind of behavior all the time. So to kind of lend credence to the argument, because we haven't done this yet, on the left is a big snapshot of atmospheric river in the Pacific that is from this paper down below. And what these people did is they calculated the finite time Lyapunov exponents associated with the whole picture, not just the atmospheric river. And you can see the atmospheric river actually pops out. It's the local maxima in all the Lyapunov exponents. So what that says is that a small perturbation will grow quite rapidly in that particular area, and hence this is a good place to start messing around with, rather than trying to move the mountain. Okay, how do we, every time I give this kind of a talk, people say, how are you actually going to provide the energy to change this? One of the colleagues here said, oh, you're going to blow up hydrogen bombs to do this. I was going, that's not the idea. Just to clarify where he got that idea is that the people who were trying to control hurricanes, they calculated the total energy in the hurricane system, and then they calculated the total energy it would take to squash that. And it was in the tens of terawatts to do something. So that was hopeless. Here we are not trying to do anything like that, is the idea. So we have to still think about what we do. And so one of the thoughts is that if I look at a typical thunderstorm, what's the amount of energy dissipated by that thunderstorm? It's typically in the order of 10 gigawatt hours. So it's substantial, basically. If I do cloud seeding or other interventions to generate a rainfall, I need a lot of humidity. When people try to do cloud seeding in the desert to produce rainfall, there isn't humidity. They're trying to force the issue. This is a different situation. I'm looking at something that's carrying the most moisture possible in the atmosphere. So intervening in that particular way here is possible, and you're doing that intervention over the ocean, is the idea. So there are several things. Some of them just sounded completely wacky to me, but I've included them. There's a group in China that has been taking large speakers, audio speakers, and pointing sound waves at the atmosphere, and they claim that there's a 17% increase in precipitation by putting 50 decibel noise up. I would love to see this happen. We were criticized by one of their colleagues who said that these people need to replicate their experiment hundreds of times before we will believe it. So they have published 3 papers since then showing statistical evaluation of their results, and they claim to do it. They provide some physics-based arguments. There's people at the University of Geneva who've been doing these laser experiments, and these are high-powered lasers. So what I found really fun about their story was they point the high-powered laser, which attracts all the lightning. So they focus a lot of energy into a small area. And then they use low-powered lasers to detect the collisions of the water molecules to figure out what the induced rain rate is. So as time gone that, this is pretty exciting stuff. But I don't know if any of these things will work. The third idea that's been pointed out is space-based microwaves. So you can actually generate enormous amounts of energy and actually focus it very narrowly if you wanted to do that. And the nice thing about that one, if it were practical, is that if I have stationary satellites in geostationary orbit, I could basically do this wherever. So if I need to do an intervention here and the next intervention is half the way across the Pacific, it's doable. So that's kind of the idea. So to summarize, what's the potential? I don't know. This is an idea that I've had for some time. It opens up a new area of research for people, which is a different way of thinking about it. I do think there's a need for developing weather control technologies. Theoretically, it seems possible. We have a specific first target. I would love to do hurricanes, but I want to see if we can do something with the atmospheric rivers first. So our goal is to first demonstrate this with numerical modeling of the realistic case. And then in parallel, work on understanding what are the physical mechanisms for perturbation. Who else is doing this? Unfortunately, not very many people. There is a project in Japan called Moonshot 8. So Boyan and Shin located these people at AGU, zoomed in on them like vultures, and now we are working on a collaboration with them. They got, I think, $2 billion for this wonderful project. I would think President Trump would be very happy to give us the same amount of money. And UAE has a little bit of work, and China has some work. And that's about it at the moment. So thank you for listening. This is the storyline, and I would love to see if anybody wants to get involved.